Yes, Gulab, we can start.
Hello, I'm Gulabchand Dewangan. I'll be giving two talks. Today is the first talk, and the day after tomorrow there is another talk. So today I'm going to talk on active galactic nuclei. So these are some of the books which I have listed. If some of you are interested to know more about active galactic nuclei, you can go through these books, particularly the book listed here by Broadley and Peterson is an introductory book. And if you are going to start working on the field or want to know more, you can actually read this book. So first question, what are active galactic nuclei? Here you see the photographs of two galaxies. One of them in the left side is an active galaxy NGC 5548, and in the right side there is a normal galaxy NGC 3277. So how do we identify whether a galaxy is an active or a normal galaxy? So imagine taking a short exposure of a galaxy, and if it is an active galaxy, what you will see is a bright point star-like object, and you would not see anything else. While in a normal galaxy, if you take a short exposure, you may not see anything. But if you keep on increasing the exposure time, you will start seeing in case of active electric nuclei, the bright point-like source will become brighter and brighter. And if you keep on increasing the exposure time, then you finally start seeing the host galaxy, which may be a spiral galaxy or an elliptical galaxy. In case of normal galaxy, as I mentioned initially, you will not see a point source, but if you increase the exposure time, then you will start seeing and the galaxy, the normal galaxy, which may again be a spiral galaxy or elliptical galaxy or any other type of galaxy. So the active galaxies or active galactic nuclei are identified by the presence of a very bright point-like or a star-like object at the center of a galaxy. Active galacti are not only identified by the nuclei, bright nuclei at the centers, but also by some other observational characteristics. For example, one may observe in some active galaxies a jet-like feature originating from the nucleus. In this picture, you see there is a bright nucleus, and then there is a jet coming out of it. This is again a sure shot signature of active galactic nuclei. So essentially, the active galactic nuclei are nuclei of galaxies that are active in some sense. And what is this some sense? An energy source that is other than the stars. So these are called AGN if the activity is substantial in some characteristic determined observationally. For example, very bright nucleus or the jets from nuclei, or even we will see the other observational characteristics. For example, broad emission lines in the optical and ultraviolet region. This is another example of an active galaxy. Sometimes you may not see very bright nucleus at the centers in the optical or in ultraviolet because the center there are obscuration by dust lens or the host galaxy material. If you take a picture in X-rays, particularly slightly at medium or harder X-ray energies, you will see very bright nucleus in the X-rays, and that bright nucleus in the X-ray is again a sure shot signature of the presence of an active nuclei in a galaxy. There are a number of types of active galactic nuclei, but essentially all of them can be put in three major categories. One of them is called Seyfert galaxies. They are hosted, these nuclei, active nuclei in Seyfert galaxies are hosted by spiral galaxies, and where the luminosity or the power output from the nucleus itself is comparable to the luminosity of the entire galaxy consisting from huge number of stars. Then there are radio galaxies. So radio galaxies are again active galactic nuclei, but they have very strong radio emission. The Seyfert galaxies, they also have radio emission, but the amount of radio emission is much, much smaller compared to the radio galaxies. The radio galaxies are also called radio loud active galactic nuclei. In addition to Seyfert galaxies and radio galaxies, the third type are these quasars. which stands for quasi-stellar radio sources. Quasars can be both radio-quiet as well as radio-loud objects. They are often found in elliptical galaxies. They are much luminous or more powerful compared to both Seyfert galaxies and radio galaxies. The power output from the active nucleus itself from quasars could be 100 times the luminosity of the host galaxy. So therefore, they are about a factor of 100 more powerful compared to Seyfert galaxies and Seyfert galaxies, for example. Seyfert galaxies are mainly identified by their optical spectrum. So here you see this optical spectrum. In the upper panel, you will see the optical spectrum. First of all, you see the continuum is very strong. Almost all active galactic nuclei have strong continuum. On top of that, there are a large number of emission lines. First of all, you see some of the lines are broad emission lines. For example, the H alpha in the rightmost corner, then there are H beta, H gamma, etc. Okay. In addition to the broad emission lines, there are these narrow emission lines. For example, oxygen 3 at 5,007 angstrom. And if you look at the width of these lines, you can convert that into in velocity units by using the Laplace formula. So the line widths for the broad emission lines is typically of the order of 5,000 kilometers per second. What that means is that this line emitting material is actually moving with these about 500 kilometers per second speed. And the narrow emission lines have a width of about 500 kilometers per second. So these are much narrower compared to the broad emission lines. And in the bottom panel, there is a zoomed in version of this spectrum to show the features near the continuum. First of all, you will notice at the blue word of the spectrum below about 4,000 angstrom, there is a rise in the spectrum. So this is called the small blue bump. And this arises due to the Balmer continuum from hydrogen, as well as a large number of transitions from singly ionized iron atom. So these two features, the Balmer continuum and the large number of emission lines from the iron they constitute this the small blue bump. So the next type is the radio galaxies. Let me briefly tell you about the radio emission, how the radio emission was discovered and how the AGNs were identified. So the radio emission was discovered from our galaxy by Jansky in 1933. And this turned out to be a power law in the spectral form, and there's a high degree of polarization. This is a characteristic of a synchrotron radio emission. So the radio emission from our galaxy is essentially due to the synchrotron process. And because the synchrotron emission arises due to high energy particles, high energy electrons, which are moving in magnetic fields. So therefore, the role of high energy particles and cosmic magnetic fields were realized very quickly. And that's how the high energy astrophysics started born. So after the discovery of radio emission, the subsequent radio surveys revealed a large population of galactic as well as extragalactic radio sources. Some of the famous ones are the radio source Cassiopeia A, which is associated with the young supernova remnant. The other the source is Cygnus A. The radio source Cygnus A was identified with a galaxy at a redshift of 0.057. So what is this guy? What is Cygnus A? Let's look into detail. So the extragalactic source Cygnus A was found to be more powerful than million times the radio emission of our galaxy. Our galaxy has radio emission due to the supernova explosion, supernova remnants. But Cygnus A, the galaxy the radio galaxy was something like million times more powerful than the radio emission of our galaxies. So something strange was going on. Later on, when this radio images were studied, they showed this double lobe structure. So you see there are this double huge lobes at the two ends, and near the center there is a core or a very nucleus. This nucleus actually coincides with the optical nucleus of the galaxy, and there are these jets emanating from the nucleus which connect to the lobe, and which essentially these jets interacting with the intergalactic medium form this radio lobes. So this is completely different morphology compared to a normal galaxy. So these are the peculiar characteristics of radio galaxies. So what are radio galaxies? Essentially, galaxies associated with bright radio sources. They are very much more powerful radio emitters than our own galaxy Milky Way. Radio power or low radio power, something like less than about 10 to about 23 watt per hertz, is common in normal galaxies like our own. And as I mentioned, the origin of this radio emission is the synchrotron emission in supernova remnants. Powerful radio galaxies have power. Radio power is more than about 10 to about 25 watt per hertz, and the weak radio galaxies have power in between these two numbers. So, and later on, when people have studied the most powerful radio galaxies, they found that the most powerful radio sources are associated with optical star-like objects. They are called the quasi-stellar radio sources or quasars. Here is the discovery, how the discovery of this quasars actually happened. So this is an optical image of a quasar called 3C273. This is the 73rd radio source in the Cambridge catalog of radio sources. And you see this is just a star-like object. So for example, in the field, there are other stars, and this quasar also looks like a star in the optical images. When this optical spectrum of 3C273 was studied, there were surprises. First of all, there were line emission, but the lines were not found at the locations or at the wavelengths of what is known at the laboratories. Later on, people found out that the 3C273 also emits the well-known emission lines. For example, the Balmer lines S beta, S gamma, S delta, etc. But these lines were at distant wavelength, and people later on found that these lines are actually rate shifted by large amount. So this is the comparison spectrum from the laboratory, and you see the S delta line or S beta line shifted by large amount compared to the line positions in the laboratory spectrum. And what is so special about this redshift? The redshift for this 3C273 was calculated to be 0.158. So what is so special about this high redshift at that point of time? So using the Hubble's the expansion of the universe, this is essentially the Hubble's formula. One can convert the redshift into distance, and in this case, it turns out to be a distance of 470 megaparsec, which is about 1.5 billion light years. So the light from this quasar takes about 1.5 billion years to reach us. And if it is at a large distance, and if we are still able to observe, that automatically will translate to huge power output from 3C273. One can actually calculate by what factors the power is compared to normal galaxies, for example. So one can calculate, once the distance is given, that one can calculate the luminosity or the so-called absolute magnitude. In this case, the observed magnitude is 13.1 in the B band, that one can convert in absolute magnitude in the same band of about minus 25.3 using the distance of 470 megaparsec. So this is a measure of luminosity or the power output, the intrinsic power output from this quasar 3C273. How does it compare with that of a normal galaxy? For example, what is the absolute magnitude of our own galaxy, Milky Way? So for Milky Way, the absolute magnitude is about minus 20.5, and the magnitude and absolute magnitude and luminosity are related. So one can convert these numbers. So what it turns out that this quasar is nearly 100 times brighter than normal galaxy, like our own Milky Way galaxy. So this is a huge amount of power just arising from a point-like source, 100 which is 100 times brighter than the power output from from all the stars from a normal galaxy like our own. So this is a huge amount of power. So what are the typical signatures of nuclear activity? I have mentioned a few. So let me tell you more observational characteristics of this active galactic nuclei. So they are very small in angular size, as I mentioned. They are the nuclei, and these nuclei are star-like objects. So the size of this AGNs is very small. We cannot resolve this nucleus in optical, ultraviolet, or X-ray bands, etc. So the upper one can obtain the upper limit on the size, which is much smaller than about 1 parsec or a light year, for example. So this is a bright point-like nucleus whose flux can often exceed the flux from the rest of the galaxy that I already mentioned. So the very small angular size can also be seen in various images. For example, these are examples of active galaxies, and in every case, you see very bright nuclear region. These are the images obtained from ground-based telescopes. So the resolution is not very great. So, but you see the nuclear regions are very bright and more like stars. These are some of the images of active galaxies taken with a Hubble Space Telescope. And you see, for example, the case of IC 4329, there is a very bright nucleus. In fact, in all cases, there is a very bright nucleus, and the host galaxy is clearly distinguished in these cases. And not only that, there are some features. For example, in case of IC 4329, there is a dust line passing through the central region. In another active galaxy, NGC 1019, there is a ring-like structure. So you see complex structures in the central regions, which also has a very bright nucleus. And perhaps these complex structures are carrying some clues to how the central engine is fed or triggered. Essentially, how the AGN is triggered or fed. The AGNs are not always not point-like at all wavelengths. So obviously in the optical ultraviolet range, they are point-like. Even in X-rays, they are point-like sources. But in radio, I already mentioned the huge low structure, or low and jet structures are not point-like, they are extended emission. So the peculiar morphology in the radio is just, again, a signature of active galactic nuclei. So typical signatures, as we have seen, this is a large luminosity. So the luminosity can range from 10 to the power 42 to 10 to the power 48 ergs per second. That is 10 to the power 9 to 10 to the power 15 times the luminosity of our own sun. So it's imagine something like 10 to the power 9 to 10 to the power 15 suns sitting in an area which is smaller than a light year, which is smaller than the size of the solar system. And that's a huge amount of power coming out of that. That's the kind of situation, that's kind of the magnitude of power output we are talking about. So compared to that, for example, a typical luminosity of a filled galaxy, for example, our Milky Way has about 10 to the power 11 stars. And if you just multiply with the luminosity of our sun, 10 to the power 33 ergs per second. So the luminosity from the filled galaxy from all the stars in that galaxy is about 10 to the power 44 ergs per second. So if you compare with the AGN luminosities, the nuclear source can have power output which ranges from 1/100th of the luminosity of the host galaxy to about 10,000 times the luminosity of the host galaxy, that is from all the stars in that galaxy. So this is a range of power from active galactic nuclei. Of course, there are complicating factors in measuring the intrinsic luminosity. For example, large optical extinction or thick dust lens will reduce the measured luminosity. There can be also beaming, the relativistic beaming, which enhances the intrinsic luminosity. So another important characteristic of AGN is the broad band continuum emission. So again, we will have to refer to normal galaxies. So in case of the normal galaxies, essentially are pile of stars emitting a blink body radiation. So therefore, the integrated spectrum from a normal galaxy depends on the spectrum of the star, spectrum of the various stars, or the temperature of stars. Usually, there is a factor of 10 range in temperatures of the stars. So the coolest stars will have 2000 Kelvin, while the hottest stars have tens of thousands of Kelvin temperature, surface temperature. So what this means is that the power output or the spectral energy distribution for normal galaxies is confined within about 1 decade in frequencies with the near infrared to ultraviolet region. While here you see the spectrum, the solid line source, the spectrum of normal galaxy. So obviously you see the spectral energy distribution is confined to from 10 to the power 13 hertz to about 10 to the power 16 hertz or so. While these points, these are the filled circles, show the spectral energy distribution of a Seyfert galaxy. Now you see in the radio region also there is the emission from AGN, and in the ultraviolet beyond the optical region there is a strong ultraviolet region. Not only ultraviolet region, there are X-ray emission as well as gamma ray emission. So the spectral energy distributions of AGNs are spectacularly different than normal galaxies. And if you consider this quantity nu f nu, so nu f nu is essentially the amount of flux per decade in frequency, and that number turns out to be roughly constant between infrared to gamma rays for radio quite AGNs. So this also means that the spectrum, which is represented as the flux density, is a function of frequency that will be more like a power law with an index of -1. This is another example of a spectral energy distribution of an AGN. This time, this is a different type of AGN, so-called blazars. So the blazars are AGN which have very strong relativistic jets, and these jets are thought to be pointed towards us. In this case, you see the emission is very strong from radio to infrared, optical, UV, up to gamma rays. They are much brighter than Seyfert type agents, in fact. So, as I mentioned, the broadband continuum emission is an important characteristic of active galactic nuclei. Then some of the AGNs, so very strong emission lines in the optical and ultraviolet. If you here, I'm showing the spectrum of different types of AGN as well as the spectrum of a normal galaxy. In the left bottom panel, you will see the spectrum of a normal galaxy NGC 3368. So first of all, you see this spectrum is noisy. Usually this kind of spectrum the noisy spectrum arises due to the low flux. So the continuum flux is low. That means the object is pretty weak. If you compare the spectrum of normal galaxy with a spectrum of the Seyfert 1 galaxy, for example, the top right panel NGC 4151. In the case of normal galaxy, you see the absorption lines. These absorption lines are essentially due to the stars in the host galaxy. While in case of ATN, like Seyfert 1 galaxy, NGC 4151, you see very strong emission lines. There are, as I had mentioned, there are two sets of emission lines. One is the broad emission line, the other one is narrow emission lines. But then there are other types of AGN which only show the narrow emission lines. So the AGNs which show only narrow emission lines, they are called Seyfert 2 objects, and AGNs which show both broad emission lines as well as narrow emission lines, they are called type 1 or Seyfert 1 object. The radio galaxies, which I mentioned to you, they also show emission lines in their spectrum, and they also show both narrow and broad emission lines. The ones which show both broad and narrow emission lines are called broadline radio galaxies, while those showing only narrow emission lines are called narrow line radio galaxies. The important thing is this mean quasar spectrum. This was constructed by merging spectra of large number of quasars. So this is the typical quasar spectrum. The continuum is blue. The continuum essentially rises towards a shorter wavelength or towards bluewards. So the quasar continuum is essentially blue. Then there are other types of AGN, which one of them I mentioned is blazars. So they show very, very strong continuum, but the spectrum is almost featureless. In this case, as I had mentioned, these objects have relativistic jets which are pointing towards us. So the jet emission essentially dominates any other emission components, and therefore you do not see strong emission lines in the case of blazars or this BL-like kind of objects. In addition to these features, the active galactic nuclei so strong X-ray emission, as well as some of them show gamma ray emission as well. I'll discuss X-ray emission from AGN in more detail later. There's another characteristic, observational characteristic of AGN, which is very important, and that is variability. Most AGNs are strongly variable at almost at all bands. For example, here are the light curves of AGNs at different wavelengths. What are the light curves? These are essentially the flux as a function of time. How the flux is varying as a function of time, the light curves measure this particular feature. So in the top left panel, you see the light curve, X-ray light curve, essentially X-ray intensity or X-ray count rate is a function of time in days. And you see this is highly variable. Just a minute. So you see this X-ray light curve where the AGN IRAS 13225 is highly variable. Very rapidly it is varying on scales of days. In fact, if you see the light curve at shorter time scales, the AGNs are highly variable, even on thousands of seconds or so in the X-ray band. In the top right panel, this is the light curve of line emission. So for this AGN NGC 5548, so you see the carbon 4 line emission, how the carbon 4 line emission is varying, how the Lyman alpha line is varying, how magnesium 2 line is varying. And in the bottom right panel, you see the continuum UV emission. So the continuum at 1350 angstrom, how it is highly varying. Continuum at 1840 angstrom, similarly 2670 angstrom. So what you observe in the optical spectrum, the continuum as well as the line. So the both continuum and line are actually highly variable, and this is very helpful in measuring black hole masses of active galactic nuclei. This in the bottom left panel, this is the light curve of the radio emission. This is 30 centimeter radio intensity is a function of time. Again, you see very strong variability from a blazar, this BL Lesseté object. As I had mentioned, some of the AGNs are radio loud. They have very strong radio emission. Typically, 10 to 15% of all AGNs are actually radio loud. And here again, I'm showing Cygnus A. So this morphology, first of all, there is a core, a point-like the structure, the core structure, which coincides with the optical nucleus. Then there are the jets emanating from this this nucleus or the core, and these jets actually are in the both sides, but sometimes we are not able to see, or only we see one-sided jets. And these jets connect to these lobes and the hot spots. So typically, the size of this core is milli-arc second. Then, and the sizes of these jets are from parsecs to kiloparsec scale, and the size of this hot spots itself is of the order of kiloparsec scale, and the sizes of the lobes are hundreds of kiloparsec, or even larger than that in some cases. This is a typical morphology of radio galaxies. In radio sources, there are three distinct regions in the radio sources. One of them, as I mentioned, the diffuse lobes, which extend to kiloparsec to megaparsec scale. Then there are narrow jets which connect to hot spots at the edge of these lobes. At the center, there are these compact sources coinciding with the nuclei. In some radio sources, you see the core, and there will be this blobs near the core, and the blobs are actually observed to be moving. For example, in this figure, this is the observation of 3C273 as a function of time, from July 1977 to July 1980. And you see this blob was ejected from the nucleus, and then as a function of time, the blob is moving, and you see the separation between the core or the nucleus and this blob is actually changing or actually increasing. In November 1978, there seems to be another blob being ejected. So with the time, this source is moving out, and therefore one can actually measure at what speed these blobs are actually moving. When people did that, there is a big surprise. In this case, 3C273, this blob appeared to be moving at 8 times the speed of light. But you may be surprised. How is it possible that something will move faster than the speed of light? This kind of things actually does not violate the principle of special relativity. It's I'll just explain you. And this is called superluminal motion. If the blob is moving with the apparent speed more than the speed of light, the such motion is called superluminal motion. Imagine this figure, this cartoon diagram. In the right side, you see the an AGN. Let's say at time t equal to 0, a blob is ejected. So that information reaches to the observer at time t, which will be the distance divided by the speed of light. So that is t is equal to d by c. Now imagine at time t1, a blob is ejected after time t1. Let's say the component is located. So at time t equal to 0, this blob was ejected, and after time t1, this blob travels, and it is located at a distance of v times t1. So v is the speed, and the t1 is the time. So the and this will have a projected distance of v t1 sine theta. If this theta, where theta is the angle, this blob, the direction in which the direction it moves, makes this angle along with the line of sight. So this particular information that the blob has reached to a projected distance of vt1 sine theta by this is observed by an observer at a time which is t2, that is t1, because after time t1 this blob reaches to this distance, travels this distance vt1, and this information from this blob to reach to this observer, which is d minus vt1 cos theta, which this is projected along the line of sight, is this vt1 cos theta. So that distance you need to subtract from the actual distance d minus vt1 cos theta divided by c. So therefore the transverse speed of this blob would be vt1 sine theta, that is the projected separation, and the time difference t2 when the observer comes to know that blob has moved this transverse distance, minus d by c when the observer knows that this blob was ejected. So if you do a little bit of algebra, then you will see this transverse speed is given by v sine theta divided by 1 minus v cos theta by c. So one can maximize this transverse speed with respect to theta. And you will get cos theta equal to v by c, and v perpendicular, or the transverse speed, is Lorentz factor times the speed of v, because the v can be very large but below the speed of light. But because of this, if the v is close to c, then this Lorentz factor can be very large. So the Lorentz factor times the speed, which is already close to c, that can give rise to very large apparent speed, larger than the speed of light, and that's how you observe the apparent motion of this blob more than the speed of light without violating special relativity. I already mentioned this. So let's we have already looked into this observational characteristics, and let's see what is the power source of active galactic nuclei that gives rise to huge power from a tiny region. So if you think of the total energetics. So you would like to have what is the total energy output from AGN. So you can roughly approximately calculate this quantity. First of all, roughly 1 out of 100 galaxies is an AGN. So you can argue, okay, maybe all galaxies go through the AGN phase, but then they survive something like 10 to the power 8 years, given that the age of the universe is about 10 to the power 10 years. So for a bright AGN, which emits a luminosity of about 10 to the power 45 ox per second, and if it lasts for 10 to the power 8 years, then the total energy output is going to be 10 to the power 61 ox from an AGN. The same, this calculation can be done in much more realistic manner by looking at the radio emission, because the radio emission arises from the radio emission essentially due to the synchrotron emission from the electrons which are in the lobes, and these electrons have high are large energy. So one can, based on the spectrum of the synchrotron radiation, one can measure the energy spectrum of electrons and the strength of magnetic field around in which the electrons are moving and giving rise to the synchrotron radiation. So when you combine the total energy of electrons and the energy of the magnetic field, that number again turns out to be 10 to the power 61 Earths. This is the total energy in the lobes. So these numbers essentially are more or less consistent from two completely two different techniques. So the question now we had to worry about how there's such a huge amount of energy, 10 to the power 61 ergs, is generated from these agents. So let's look at in little more detail. So of course we cannot resolve the nuclei, the AGNs, but we can use another argument, essentially the argument based on time variability. So time variability also is a measure of the size of the emission region. So let's say how one can use the time variability. So assume that the state of the emission region is changed by a physical process. If there is a variability, so something has to change. So let's say the state of the emission region is changed by a physical process which is giving rise to this emission. So then there are two time scales which are important. One is the T process, which is essentially the time scale for the radiation process. And then another time scale, delta T, this is the crossing time needed to cross the emission region. So you can imagine like a spherical region. So something, the state of the region at the center maybe first changed, and that initiates the variability. And because the variability is by a factor of 2 or more, let's say, so then the entire emitting region has to participate in this variability event. So the disturbance which initially arises at the center of, let's say, spherical region, that has to travel with some speed in order to cover the entire emitting region. So this crossing time, let's say this is delta T. Usually the time scale for this crossing is much more than the time scale for the radiation process, which is very short. So if the state change travels or spreads with a speed, of course the speed has to be less than the speed of light. Then the size of the emitting region, you can easily write down the size of the emitting region L equal to the speed with which this disturbance spreads into the crossing times, delta T. With this quantity definitely must be less than the speed of light times this crossing time. So for the observed time scale of the variability, which we call, let's say, T observed, that T observed will be the sum of the time scale for the radiation physical process or radiation process plus the crossing time. And as I mentioned, the T process is much smaller than the crossing time. And you can always write, in any case, the size of the emitting region is either equal or less than about the C times the observed variability time scale. So if you have the variability time scale multiplied with the speed of light, that gives the upper limit on the size of the emitting region. So let's see from observations what we infer. So in the optical UV band, the observed variability time scale is roughly about 1 to 10 days, and that corresponds to a size scale of about 0.001 to 0.01 parsec. It's a very compact region, much less than a light year. in the X-ray band, if you look at the variable time scale, it is even much shorter, on about an hour, for example. This corresponds to a size scale of about 10 to the power minus 5 parsec. It's very, very tiny region on astronomical scales. So if you compare this size scale with the radius of the Schwarzschild radius, for example, which is given by 2gm divided by c square. So you see here, for 10 to the power 6 solar mass black hole, the size of the Schwarzschild radius is 10 to the power minus 17, 10 to the power minus 7 parsec, while for 10 to the power 8 solar mass black hole, 10 to the power minus 5 parsec. This compares well with the X-ray variability time, the size inferred from X-ray variability time scale. So maybe this gives rise to a possibility that maybe we are observing X-ray radiation from the vicinity of a supermassive black hole. So the people investigated after the discovery of agents. People investigated what the reason behind the huge amount of power, and let's look into the arguments which led to the current understanding of AGN. So obviously, because stars are powered by nuclear fusion, so people obviously investigated whether maybe the nuclear fusion is responsible for a huge amount of power from AGN. So the total energy output from a quasar is at least the energy stored in the radial lobes, which is 10 to the power 61 arcs. And if you want to generate this 10 to the power 61 arcs by converting the material into energy, then you will need something like, you'll need to burn 10 to the power 7 solar mass completely with 100% efficiency. Okay, but of course we cannot have 100% efficiency. For nuclear reactions have the efficiency about 0.6% for hydrogen burning. So if you want to produce 10 to the power 61 ergs by burning or by completely converting 10 to the power 7 solar mass, then you will need to start with 10 to the power 9 solar mass material. If you burn 10 to the power 9 solar mass material, then you will end up converting 10 to the power 7 solar mass completely into energy, and thereby producing 10 to the power 61 ergs. And now, from the rapid time variability, we know that the typical AGN is no bigger than our solar system. So that means the entire 10 to the power 9 solar mass, a huge amount of material, must be confined into a tiny region of the order of the size of solar system. But if you are, let's say, collecting the huge amount of material, 10 to the power 9 solar mass, into a tiny region, then you can find the gravitational energy release from such a thing will be this 3 by 5 gm square by r, and if you put the values there, then you will get 10 to the power 62 ergs total energy, and this is 10 times larger than the nuclear fusion energy. So in this process, the gravitational the energy release as a result of the gravitational contraction, you can produce much more energy compared to what is possible from nuclear fusions. Therefore, in 1969, Donald Lindenwell made up this famous statement. He said that evidently, although our aim was to produce a model based on nuclear fuel, we have ended up with a model which has produced more than enough energy by gravitational contraction. The nuclear fuel has ended as an irrelevance, and that's how the gravitational contraction, the gravitational accretion of material onto we'll see onto a black hole came into picture. So how do we, before we say there is a huge mass or a black hole, we need to see how do we find the masses in AGNs. So we can find the masses of AGNs using this Eddington limit argument. So what is this? Any object cannot have arbitrarily large luminosity, because if it produces huge amount of radiation, then the radiation pressure will throw out the material. So therefore, the object will not be stable. So in a way, one can use, by measuring the luminosity, one can measure one can have an estimate of the mass, because the inward pull of gravity and outward radiation pressure force have to balance. Otherwise, object will not be stable. So let's see how one can calculate the Eddington luminosity. So imagine there's a huge mass, this mass M, capital M, and at a distance r, there is a small mass m, which is being accreted onto the large mass design mentioned with capital M. So the inward there is an inward gravitational force F gravity, and there is an outward radiation force due to the radiation. So accretion rate is controlled by the momentum transferred from the radiation to the small mass m. So as I mentioned, the gravitational force is gmm by r square, and the outgoing photons from this mass m, those will scatter the small mass m. And let's see what is the radiation pressure force due to this scattering. So let's say this L is the accretion luminosity, the luminosity from the capital mass m. So if L is the luminosity, then the number of photons crossing its radius r per second per unit area is L divided by 4 pi r square, and that will be the energy per unit area, and it divide by the energy of individual photons, h nu. That gives you this the number of photons crossing at r per second in photons per meter square per second. Okay. And the actual scattering is determined by the cross section. In this case, Thomson scattering cross section, because the scattering of radiation by free electrons is essentially Thomson scattering. So, therefore, from this, the number of scattering per second, you will just have to take this sigma t, the Thomson scattering cross section, and multiply with this number of photons crossing at r per second. So, therefore, you get the number of scattering per second is L divided by 4 pi r square h nu multiplied by the Thomson scattering cross section. And in each scattering, the momentum transferred from photon to particle is essentially h nu by c. And we know that the momentum gained by particle per second, or the rate of change of momentum, is essentially the force. And this is and therefore the radiation pressure force is this number of scattering per second multiplied by the momentum transfer h nu by c, and you get the radiation pressure force L sigma t divided by 4 pi r square c. And when you equate these two, the radiation pressure force and the gravitational force, you get the Eddington luminosity. And once these two forces are equal, at this point, accretion essentially stops, effectively imposing the limit on the luminosity. And this limit on the luminosity is the Eddington limit, which is given by 4 pi c g. This is the capital mass m of the object which is accreting, and m is the mass of the material which is being accreted onto the mass capital M divided by sigma t. So what should we use for the mass small m? Okay. So we are talking about the accretion of material, and material of course is electrons and proton. So first of all, the electrostatic forces between electron and protons binds them together. The scattering is on electron, but because of the Coulomb coupling, the both proton and electron will move together. So therefore, for the small m, we should use the sum of the proton mass and electron mass, which is almost equal to the mass of the proton, because mass of the electron is much small. So therefore, one can calculate the Eddington luminosity, and this turns out to be about 1.2 into 10 to the power 38 ergs per second for one solar mass object. One solar mass is 2 into 10 to the power 33 grams. So for one solar mass object, 1.26 10 to the power 38 ergs per second. Now, if you compare this with the luminosity of our sun, which is about 10 to the power 33 ergs per second. So sun is obviously very sub Eddington. Okay, so because the observed luminosity must be less or equal the Eddington luminosity. So given the luminosity of, let's say, something like 10 to the power 46 ergs per second for luminous AGNs, the mass must be more than 10 to the power more than million solar mass. Okay. So once we have these arguments, we can put into this argument and make a case for accretion onto supermassive black holes. First of all, these high luminosities, we infer from high luminosities, we infer Eddington limit. That's using the Eddington limit argument, we infer large mass, more than about million solar mass. And these AGNs are highly variable, X-ray variability on hours time scale. So, that implies a very small source or very compact source. So the huge mass is sitting in a very compact region. So in physics, we don't know anything other than a supermassive black hole, other than a black hole which can have these properties. So we say that there is a supermassive black hole with mass more than 10 million solar mass, which is accreting material and generating huge amount of power, which we are observing in different electromagnetic bands. So, just to keep in mind, these are the typical numbers. Central supermassive black hole, which has a mass 10 to the power 5 to 10 to the power 10 solar mass. Then this powered by accretion with an efficiency eta, which converts the accretion rate into luminosity. Size scale is of the order of, let's say, Schwarzschild radius. The luminosity is of the order of Richter luminosity. Lower than that, of course, Richter luminosity is given by this quantity. I think I will stop here and take questions.
Gulab,
Yes.
did you get any question in the chat window? Because nobody has raised a hand.
Oh, okay. Just a minute. Yeah, just let me see. I'm seeing the chat window. Yeah, I see what some of the participants have asked for the slides, which we will share. There is one question by Madhusudan Purohit, and he's asking, will AGN of any galaxy be active throughout its lifetime of that galaxy, or it may become inactive and may cool down? So as I mentioned, of course, we do not have the opportunity of looking at AGNs over all its time scale. From the fraction of AGN of all galaxies, which what we find is roughly 1% of AGN, 1% of all galaxies are AGN. So from that the statistics, we can say that the typical time, the lifetime of AGN should be about 10 to the power 8 years. There are observationally there are evidences of recurring AGNs. For example, the AGN activity was there for, let's say, for a million years or so, and then it became inactive. But then there's something else happened, which is something triggered the AGN, and again it became active. So though there are some observational evidence to that. So the AGN may become inactive and then reignite or get triggered again. It is possible. Yeah, so there is another question. Can you please repeat Eddington luminosity for the sun? So for a solar mass object, the Eddington luminosity is about 1.2 into 10 to the power 38 ergs per second. Compared to this, the actual luminosity of sun is 10 to the power 33 ergs per second. So Eddington luminosity is roughly 5 orders of magnitude larger compared to the observed luminosity of sun. There is one more question. Can galaxy mergers or interactions create AGN? Yes, galaxy mergers are in fact thought to trigger active galactic nuclei. So a number of participants have asked to share the slide. So Santosh, how do we share? How do we?
So Gulab, you send the slides to Asim. He will put it.
Okay, all right. I will send that.
So Gulab, there is a one hand there. Paramita, I'm just unmuting her.
Yes.
Yeah.
Hello, sir.
Hello. Yes.
So my question is, in the initial slide, I think slide 7, you showed that the spectrum of the quasar and that we have converted the wavelength into, I think, velocity shift.
Right.
So how do we do that? First question. And second question is, what is the need to convert wavelength into velocity shift? Like, which is better parameter to judge wavelength or the velocity shift?
Yeah, so first of all, we use this Doppler shifts. Whenever we can, from the spectrum, we can measure the width in wavelength. Okay, but in order to interpret that, what is causing such a width? If it were narrow, then we would not worry. For example, let's say a gas at some certain temperature, 5,000 Kelvin or so, and if the gas, just because of the temperature, the gas molecules will be, or atoms will be moving around, and that will give rise to the width. Okay, but if you calculate those widths are much smaller. These compared to the width which we observed in AGN. Then we use this Doppler shift and convert into velocity units, because of the from all other arguments we see there is a massive object at the center, the massive black hole. So therefore the material must be moving around, and that material which is moving around the black hole is giving rise to this large velocities, and therefore the large width. So therefore, obviously converting into the velocity units compared to the wavelength width, that is the velocity units much better here. The other question, can you repeat?
So this was my question, that velocity shift, or how do we convert it, like from wavelength to velocity shift? What is
Yeah,
the
using
formula?
using the Doppler shift, the velocity, when the velocities are non-relativistic, in that case, if the wavelength width is delta lambda, essentially the full width at half maximum of the line profile. So if you have a line profile which looks like a Gaussian profile, you can measure the width in terms of full width at half maximum in wavelength units. So you can convert that into speed by just using the formula of Doppler shift, which is delta lambda. This is width. Divide that by the line centroid wavelength, which is lambda, multiply with the speed of light. That will give you the velocity width from wavelength width.
Okay, thank you, sir.
Okay, Gulab, I think so. There is no other question from
Yeah.
the participants.
Yeah, thank you very much. So we will share the slides.
Thank you.
So I can sign off, Santosh.
Yeah, sure. Thanks.